All right, welcome back everybody to the afternoon, the second and last half of the SGP Graduate School. I hope everybody found some way to cool down in the middle. Be sure to drink enough water. Second point as a reminder is before you ask a question, please wait for the microphone. This is not for the rest in the room, but it's for the recording. So that everybody, when they look it back, they know what the question was that the speaker's responding to. So that is why, to remind you, is wait for the microphone. With that said, I want to introduce the next speaker. This is Nathan King from Shaper, talking about closest point geometry processing, and very much looking forward to it.
Thank you. Thanks everyone for coming, and thank you for the invite. So, digital objects can be created in many different ways. For example, LiDAR scan sensors can be used to create the digital world surrounding a self-driving car. Researchers, engineers, and artists can use software like Houdini, Shaper 3D, or Blender to manually create objects. Also, functional descriptions of objects can be used. For example, all the points that satisfy this equation will give you this surface. With the numerous object creation techniques come just as many ways to represent an object on a computer. For example, as a mesh, a point cloud, a parametrization, or a level set. Algorithms that are specialized to each specific representation have the advantage of being able to use properties from that single representation. For example, sign distance fields are great for collision detection. Parameterizations are convenient for texturing an image onto a surface. And GPU hardware was developed with meshes at the forefront. However, in large pipelines, it is common to have to transfer between different representations for different algorithms, which results in conversion errors in your pipeline and also costs computational time. For example, you could use a sensor to capture an object as a point cloud, transfer it to a mesh to do some geometry processing algorithm like stylization transfer, and then map that to a parametrization to be able to put an image on the surface. You could also have pipelines that require combining multiple different types of objects. For example, you might want to combine a point cloud and a sign distance field into some method E, like a physics simulation. And in this case, there's no specialized single representation that would work without conversion of at least one of these. So it would be great if you had a unified framework that could handle all desired applications and all object representations. And I think closest points provide a good candidate for this unified framework. So given some query point x in the space surrounding your object S, the closest point is the point on S that it has the minimum Euclidean distance to the point x. So here are some closest points for the black query points surrounding this object. And closest points are really nice because they can represent really general manifolds, such as this closed and orientable object. But it can also be open and unorientable, like the Mobius strip, or even mixed codimensional, so you can have like these 1D curves attached to a 2D surface, all of it embedded in R3. Also, closest points provide a representation that is actually both explicit and implicit, which is quite a distinct property. Other representations usually are one or the other. So meshes, point clouds, and parameterizations, those are explicit representations because they specify points on the actual manifold. Whereas level sets or sign distance fields, they provide an implicit representation of the manifold where you have this implicit equation f of xyz equals 0, and that defines the points on the manifold. The closest point mapping itself is that takes points from the surrounding embedding space Rd to the manifold is an implicit representation. You can get like the traditional scalar field implicit from this, although it's unsigned. You're just getting the distance field between x and its closest point. And you can also get a vector valued implicit representation because you know that for any x on the object S, it must be its own closest point. Meanwhile, the closest points themselves can be used as an explicit representation, just as a point cloud. The ability for closest points to represent many different manifold types and many different representations, along with them being both explicit and implicit, gives closest point representations a lot of potential to provide a good unified framework. Because, though, that there's so many different applications in graphics and many other fields, we decided to focus on geometry processing applications that involve solving PDEs on manifolds. Conveniently, there already existed a method to solve PDEs with closest point representations, which is called the closest point method. However, there was a main limitation to it that stood in our way to be able to apply it to many geometry processing applications. And that was that interior boundary conditions couldn't be handled. And so these are boundary conditions away from the physical boundary of an open manifold. So it can be at points or curves on the interior of the actual manifold. And they're very important in applications like diffusion curves or geodesic distance computation to a curve on your manifold. So introducing a way to handle these interior boundary conditions is basically the core of this course. But overall, I'll go through the following. So first, I'll discuss like a review of the closest point method and the continuous setting. Then I'll talk about the kind of most common way to discretize this and approximate your solution in the discrete setting. I will then discuss how to handle boundary conditions and some geometry processing applications, like the ones that this whole new framework unlocks. And I'll talk about some efficiency improvements for the closest point method in general, and finally conclude with some future directions of research. Okay, so given some manifold S and a PDE that you would like to solve on S, the problem is extended to the surrounding embedding space, and you construct this embedding PDE on the surrounding Cartesian space whose solution agrees with the manifold PDE when you restrict it just to the manifold. And so most of my diagrams, just to point out, are going to be like 1D curves embedded in 2D, but in general, this all applies to 2D surfaces embedded in 3D, for example, and even like 1D curves embedded in 3D, so higher codimensional objects. And just some quick notation, so manifold functions will be denoted U subscript S, and these will get extended onto the surrounding Cartesian space to be constant in the normal direction of the manifold, and we'll denote that with U. So to construct the embedding PDE that the closest point method solves, it relies on three main properties. So the first is the constant normal extension of U is done by composing with the closest point function. So intuitively, what this is doing is it just assigns the value of US at the closest point of X to X itself. So we call this the closest point extension. Now, if you have some function V that's constant along the normal directions of S, then the Cartesian gradient of V is going to equal your manifold gradient when you restrict just to S. And so this is because it's constant in the normal direction, so you can only have rates of change along the tangential direction. Also, if a vector field W is tangent to S and to all the level sets of S, so all these offset surfaces from the zero level set, then the Cartesian divergence is going to equal the manifold divergence at points on S. And again, it's because your vector field can only compress and expand within the tangent spaces, and so the manifold operators are equal to the Cartesian ones. And you can combine these properties to rewrite higher order differential operators with Cartesian differential, higher order manifold differential operators with Cartesian differential operators. Now these properties only hold when you have a unique closest point function. So for general S, the closest point function is rarely unique on the whole embedding space, RD. And the medial axis of S is this subset of the embedding space that has at least two closest points. Or in other words, it's the subset where your closest point function is not unique. But for smooth compact manifolds, the closest point function is always unique within a tubular neighborhood of your manifold. So this N of S is the tubular neighborhood, and it's constructed in a way to make sure you avoid the medial axis. And that's done by choosing a sufficiently small radius of the tube R N of S. The size of R N of S depends on the curvatures and the bottlenecks of your actual manifold, and the bottlenecks are thin regions in the manifold where you have like geodesically distant parts of the manifold close in Euclidean space. So this is the overall definition of N of S. So you have points X in RD that are at most R N of S away from their closest point. So let's go through an example now of how the three properties are used for the Laplace-Beltrami operator. So you have some surface function US, and you use the closest point extension to get U constant in the normal direction of S by property 1. And you know that since it's constant in the normal direction, the Cartesian gradient of U is equal to the manifold gradient of US on the manifold by property 2. And now because the gradient of U is a vector field that is tangent to all the level sets of S, all these offset manifolds, and that's because U itself was constant in the normal direction, then we know by property 3 that the divergence of this gradient field in the Cartesian space is equal to the manifold divergence. So the Laplace-Beltrami operator just gets replaced by the Laplacian of U of Cp. These principles have been successfully applied to solve all these different types of PDEs and many more. I'm going to focus around PDEs that involve the Laplace-Beltrami operator because it's one of the most common used in geometry processing. But there has been other works in computer graphics involving the closest point method and just closest point representations in general. So first off, the Euler and L solved the wave equation and Navier-Stokes equation on static surfaces. And then Euler and Westermann extended this work to deforming surfaces. Kim and L did something a little different. They increased the apparent resolution of a coarse fluid simulation, like a volumetric simulation, by solving the wave equation on the surface, basically an up-resing problem. And most recently, Morgenroth and L coupled, again, a surface PDE with a volumetric fluid simulation, but this time to simulate oil film on the surface of water. There's also been work on just visualizing closest point representation. So Euler and Westermann developed a method similar to like dual contouring and merging cubes to create a triangulation. It's better able to preserve sharp features and can handle open and unorientable surfaces. And Demir and Westermann also showed how to visualize the closest point representation just directly using ray casting. So there's actually been a couple of applications in geometry processing, but they've been measuring the similarities between like a data set of different shapes. So these applications only needed global information about the shape, and it didn't have to impose any local boundary conditions on a single shape, which is exactly what opens the door up to many different geometry processing applications. So up to now, we just discussed the continuous theory and the generality of the PDEs that can be solved with the closest point method. Most papers used a grid in the surrounding embedding space to implement the closest point method discretely on a computer. I'm going to focus on the most common grid-based approach, which uses finite differences and Lagrange interpolation. And these approximations have been chosen basically for their simplicity and that they have been well studied. And however, the continuous theory actually puts no limitation on what kind of discretization you could use. So you could also do finite elements in the embedding space and some other interpolation scheme. And there's even been papers that use radial basis functions, and we also recently developed a Monte Carlo closest point method. So the computational domain is a grid now instead of this. So the N of S was a tubular neighborhood. Now you have a tubular grid, omega of S. And so it's all the grid points that are within our omega of S to their closest point. And so in other words, so you may naively think, okay, you're extending to the surrounding embedding space. So the computation would scale with the dimension of that embedding space. However, the number of grid points actually scales with the dimension of S. So n are the number of grid points here, and dim S is, well, 1 in this case. If it's a surface in 3D, it's just a 2. Dim S is 2. And so the reason it scales with the dimension of this manifold is because our omega S is finite. And I'll discuss later how this radius is calculated. But with a finite radius, you can use Weyl tube formula to compute the volume of the tube and then approximate the number of grid points from that volume. To construct the grid with this optimal scaling, we use a breadth-first search so that we're only computing closest points near the manifold within the tubular neighborhood, and memory is only allocated as needed by using a sparse grid data structure. With this tubular computational domain now, what we need to do is approximate the embedding PDE. So this involves these approximations to differential operators like the Laplace-Beltrami operator, and that involves approximating the actual Cartesian Laplacian or other differential operators in Cartesian space, and also approximating the closest point extension. So standard finite differences are used to approximate the differential operators on the grid. For example, this is a standard 5-point Laplacian stencil shown in red that's used in 2D. And what you do is the grid points are all assigned an index, and you build a matrix that holds the weights of the stencils. So this stencil is for grid point 8. And so in row 8 of the matrix, we insert the stencil weights in the columns of the indices that are part of that stencil. So that's these columns. And the weights of the grid points themselves, they all have this factor of 1 over h squared on the front. And then the one for the center of the stencil, grid point 8. So grid point 8, column 8 is going to be -4. And then all the other ones are +1. And so you do this for all the rows for each grid point in the matrix, and you can build the full Laplacian matrix. For the closest point extension, this involves interpolation, since in general, closest points are not going to be a grid point. So here, for grid point 18, the closest point extension assigns the function value at the blue closest point, but this blue closest point isn't a grid point, so we don't have the actual function value, so it's approximated from the surrounding values on this orange interpolation stencil. And similar to the construction of the finite difference matrix, the rows for each grid point, so like this row 18, you're going to have non-zeros in the columns that are part of that stencil. In this case, it's a little different because with the finite difference stencils, you have the same weights for every single grid point. For the interpolation stencils, it depends on the query point, so the location of the closest point. So once you build the finite difference and interpolation matrices, you can approximate the Laplace-Beltrami operator as the finite difference matrix L times the closest point extension matrix E times the solution value stored on the grid, U. And then you approximate all the different differential operators in your PDE. You form the full matrix equation that you want to solve. So let's just consider an example with the heat equation. So you construct the embedding PDE, like we discussed before, to give you this. And the closest point method gives you a way to approximate the spatial differential operators. So the Laplace-Beltrami operator is approximated as the Cartesian Laplacian of U of Cp, and then discretely that's LE times U. But you also have the time derivative here, and you just use standard time stepping methods. I won't review time stepping methods here, but consider if you used explicit Euler time stepping. So your solution at time I plus 1 is just in terms of the solution at I plus your approximation to the Laplace-Beltrami operator scaled by delta t. So pictorially it looks like this, and you're just multiplying matrices and vectors and adding it together to get your new solution at I plus 1. For backward Euler time stepping, the far right ui becomes ui plus 1, and then you need to rearrange the equation and solve the full matrix equation. So instead of doing the matrix multiplication and addition, you have this linear system you need to solve. And one important thing to point out here is that the L and E matrices, when you're using them in a matrix system, there's a small modification you actually have to do to them. And I won't discuss the details of the actual modification, but the main reason you need the modification is because of numerical stability issues. And kind of stepping back a little more generally, it comes from the fact that this equation won't guarantee that your solution is constant in the normal direction. So what you end up doing is adding an extra term to penalize the solution from deviating from being normal in the constant in the normal direction. And this is the same case with stationary PDEs, so ones that don't depend on time. In both cases, you end up with some matrix equation that you need to solve in the end. And you can use direct solvers or iterative solvers. Yeah. Okay, so now that we know that we use finite differences and interpolation stencils, we can derive an upper bound on what the computational tube radius should be. So this R omega of S. I previously mentioned the fact that R omega S is finite, and that's the reason why the computation scales with the dimension of S itself instead of the embedding space. And if this wasn't the case, I mean, the closest point method would probably be too expensive compared to other methods that are just implemented directly on a mesh or a point cloud, something explicit. So to derive an upper bound on R omega S, we must figure out how far away a stencil, like a grid point in a stencil, can be in all the stencils that are necessary for the implementation. And so the furthest grid point will be at the tip of a red finite difference stencil that's centered at a corner of an interpolation stencil. And the interpolation stencils are chosen to be as symmetric as possible. So the closest point will be in the center cell, but you don't know in general where in that center cell. So to get an upper bound, we look at the distance between the furthest grid point in the center cell to the tip of the finite difference stencil, so the length of this solid black line. And if you work out the geometry there, you get this equation. So you have like the grid spacing, h, the dimension of the embedding space, d. In this example is just 2, and then p is the interpolation degree of the interpolation polynomial you're using. So it's like the spaces in one dimension of your stencil. And q is the number of spaces from the center of your finite difference stencil. Yeah, and so the size of the stencils shown here are just for illustrative purposes. They're not usually this big. What it actually depends on is the order of accuracy you want for your solution. So the only restriction is that the order of accuracy of the interpolation stencil has to be greater than or equal to the highest order differential operator in your PDE. So for the Laplace-Beltrami operator, we have to have at least second order interpolation. Yeah, and so one final detail that I didn't mention is actually how to compute closest points. So there's been a lot of work on computing closest points for different representations. Here are some examples of papers for meshes, point clouds, parameterizations, and level sets. There's even been some work on computing closest points to neural implicits. So overall, with this way of computing the closest points, if you have a closed manifold, this is all you need for the closest point method. So next I'll talk about how to impose the boundary conditions, but are there any questions up to this point? Yeah.
I was wondering when you define the radius you have around the manifold.
Yep.
Because you say you need at least enough data to compute all this operation, but at the other end you have to be away from the medial axis. But what happens if you're like sharp corner in your geometry, where the medial axis touches the geometry itself? Can you handle those cases? Does this solution degenerate? What happens?
So basically, if you just implement it the way it is now, the convergence order degrades. It basically smooths out the data going around the sharp corner. But I will talk about later, I mean, really towards the end of the course, future work on handling sharp features. But there has been a couple papers that have looked at improving it, but no one's actually fixed the core problem.
Okay, thank you.
No problem. Any more questions? Yep.
Hi. Sorry if I missed it, but when you defined the matrix for the differential operator,
yep.
Did you discuss how the boundaries are handled and what it implies, what you do for them?
You mean the boundary of the grid itself?
Yeah, of the grid itself.
Yeah. I didn't discuss it because it's not the most intuitive thing, I guess. But basically, that boundary edge, you end up getting data extended to it, and you basically remove those degrees of freedom from the finite differencing part, but they get the correct data. So that's kind of how you know how big the interpolations, because, okay, so in this figure, your finite difference stencil only ever goes to the corner of the interpolation stencil, and all the grid points, like where the arm of this red stencil sweeps, those are getting data extended also from interpolation stencils, so that all the finite differencing has accurate data. So you don't actually need any boundary condition. It's the fact that you're extending the correct data.
Okay. Yeah. And what values do you have in the matrix for these boundary points?
So nothing special has to be done for them. It's just basically what ends up happening is that they don't belong in an interpolation stencil because the interpolation stencil is close to the manifold, and these are further, and you end up with 0 columns in the extension matrix because they're not involved in the actual extension. And you can remove them from the system. So, yeah.
Yeah. Okay, thanks.
You're welcome.
I had a question about this. You had this figure where you show the samples from the grid, and it looks like some regions are higher sampled and some have lower sample counts. Is it something you need to address at all with like a mass matrix or a weighting when you solve these systems, or is it not at all a problem?
I'm not sure which figure.
Back a little bit further. I think this the previous one. So here you start to sample the points. Yeah, exactly. And so the sampling is not even everywhere.
Okay, yeah, the actual points on the surface. Yeah,
points on the surface. Is that
don't
at
do
all?
anything special for that. It's so when the convexity, depending on the convexity, the distance between the grid points will end up coming closer together for the closest points, or they'll spread apart. And yeah, there's no extra modification to handle that. Yeah.
Okay, thank you.
No problem.
Hi, Nathan.
Yep.
Just a quick question. Have you done any convergence studies for these just algorithms, or has there been any convergence studies for closest point methods and all these various PDEs that they're able to support?
Yeah, there's lots of convergence studies done. That's basically, it started in like applied math, and it from the first paper, it's been convergence studies. And I've have a lot of examples here in the talk too.
Thank you. Yeah.
No problem. Okay, I'm sure we'll have time for more questions after, but I'll just continue on now. So let's get into the boundary conditions now. So boundary conditions can come in many different forms. For example, you can have Dirichlet boundary conditions where you specify the solution value itself on the boundary, f of s. So for example, the solution value would be known on this white curve, and then you solve a PDE to get the solution on the rest of the manifold. Another common boundary condition is the Neumann boundary condition, where the gradient in the co-normal direction is specified, and the co-normal direction is not the normal of the manifold, shown here in black. It's the vector that's orthogonal to both the normal and the tangent direction of the curve. So this red curve is the co-normal. Red vector is the co-normal. And there's also Robin boundary conditions, where you have this weighted sum of Dirichlet and Neumann conditions. And there's many other types of boundary conditions. So the most common way to think of boundary conditions is to think about actually assigning them on the physical boundary of the domain itself, for example, the white curve, and we refer to these as exterior boundary conditions. But in many problems in geometry processing, the boundary conditions can be defined at points of curves away from the actual physical boundary, and these are referred to as interior boundary conditions. So interior boundary conditions can be seen throughout many different applications here. For example, diffusion curves can be used to color the surface of this dragon. The color values are specified on both sides of the curves, and they're Dirichlet conditions, so because you're specifying the actual color value. You might also want to compute the geodesic distance to this black curve, for example, or even do some vector field design by specifying a sparse set of directions. Therefore, the ability to handle interior boundary conditions is essential to unlock the closest point method for geometry processing. But before we get to the interior boundary conditions, we need to understand how you actually handle exterior boundary conditions, because the interior boundary conditions turn out that they use very similar modifications as the exterior boundary conditions. So let's start here. So the exterior boundary set is denoted omega partial s, And these are the grid points whose closest point is on the physical boundary of the manifold. So these are the purple points here, since they all have the white boundary point as their closest point. You can also think of the boundary set as all the grid points past this green normal manifold as perp going through the boundary. The natural boundary conditions of the closest point method are actually first order accurate zero Neumann conditions. In other words, if you don't do anything different from the closed manifold case with an open manifold, you'll end up enforcing zero Neumann up to first order accuracy. And this is because the closest point method extends data constant in the normal direction. So you have zero gradient in the normal direction. But wait, because I told you it's the co-normal direction, right? That really matters. That's the actual Neumann condition, is in the co-normal direction. But because grid points passed as perp, they have an undefined normal, you end up extending data constant in every direction in this half-tubular region. So you also end up with a co-normal zero gradient. Yeah. And so that's great. You don't need to do anything for zero Neumann for first order accuracy. For Dirichlet boundary conditions, you do actually have to do some modification of the equations. The exact boundary condition alpha just gets assigned to all the grid points in the boundary set. This results in a first order accurate approximation of the Dirichlet boundary condition. And so the changes necessary for the matrix representation of the Laplace-Beltrami approximation only occur in the closest point extension because there's no changes in the grid connectivity in this boundary set, so the Laplacian stays the exact same. Just the data extended onto the boundary set is changing. So first, the matrix E is assigned identity rows for all the indices that belong to the boundary set in purple. And then a second modification has to happen at the full matrix system level so that you're enforcing the equations that U equals alpha at like the full matrix system level. So A ends up getting identity rows too, and the boundaries for the boundary set indices, and B gets the prescribed Dirichlet value alpha. Okay, and so if you want to do second order accuracy, let's just first consider what would be done if you were just doing standard finite differences on a Cartesian domain. So you have some boundary that's at x0, partial s, and the Laplacian in 1D is approximated with a 3-point stencil. This one here centered at x2. But you need to slide that stencil over every grid point, so it goes to x1 also. But you can't do it for x0 because it would go inside the domain. So what you do is you introduce a ghost point, x of -1, and now the stencil can fit inside the domain, but we need data, like accurate data, to give to x -1. And we get this by using the zero Neumann boundary condition, which in 1D you just have the derivative with respect to x at partial s is equal to 0. Using a second order approximation centered about x0, you get this equation, and we can rearrange this approximation. Oh yeah, so the approximation, it just involves x of 1, data at x of 1, and data at x of -1, and you can rearrange it to get u at -1 is equal to u at 1. But the key property I want to show here with this example is that the data at the ghost point location is replaced by data at its mirror location inside the domain. So it mirrors through your boundary partial s, or reflects through. And so for the closest point method itself, grid points like this xk in the boundary set are like the ghost points in the standard finite differencing schemes. So to achieve second order accuracy, we need to extend data to these ghost points xk that is accurate enough. I will take you through the construction of what you actually do here, and it'll make more sense in the end. So what you do is so the closest point for xk is equal to your boundary point, partial s, and then what you do is you project 2 times through the direction towards the closest point to get this new point, which you can simplify to just 2 times the closest point minus xk. And then you compute the closest point of this doubly projected point. So this gives you what we call CP bar. And that's the point where you use the data at that point, CP bar, to extend to xk. And so it seems convoluted, but the reasoning makes a lot of sense when you realize that what you're doing is approximating your manifold near the boundary as a plane. Then the actual closest point on this extended manifold for xk would be this red point, and CP bar is the point reflected, it's the mirror location, an approximate mirror location reflected through the boundary. And so that's all you need to do is replace CP with CP bar in the boundary set, and then you'll get second order zero Neumann boundary conditions. For second order Dirichlet boundary conditions, we again take inspiration from the standard Cartesian finite differences. You can Taylor expand u x minus h at about x, and you get this. And in the discrete setting, you just have that u at minus 1 is equal to u at 0. So at the boundary point, minus h times the derivative, and higher order terms. We can take the second order approximation we had for the zero Neumann case and plug it in here for the derivative to get this. And then when you finally rearrange and simplify, you get that for the Dirichlet ghost points, you need 2 times the value at the boundary, x0, minus the value at x1. So minus the value at the mirror location. And so if you convert this equation in the closest point setting, just recall that we want to extend data to the boundary set points xk with assuming a planar approximation of the extended manifold. This red point is, so we want to extend it at the black point. This red point is its closest point if you're extending the manifold. The green point is its actual closest point, which is the boundary location. And this black point is the approximate mirror location, CP bar. So taking the Cartesian, just standard finite difference equation and doing that mapping, you end up with the extended data at xk should be 2 times the prescribed value at the actual green closest point minus the solution at the mirror location CP bar. And I won't discuss the details in this course, but similar ideas have been used to handle inhomogeneous Neumann and zero and Robin boundary conditions. In a paper that was just published this month, it seems. This was on arXiv in November 2025. But okay, so now I'll talk about how these ideas are used with interior boundary conditions, which is the main thing that unlocked the closest point method for these geometry processing applications. But are there any other questions now on the boundary condition stuff? Okay. So interior boundary conditions, as a reminder, they're on the interior. They're not on the physical exterior of an open manifold. So you have some boundary condition you want to impose located at some point C in white. The big problem is that now your embedding space near C is actually overlapping your manifold. Unlike in the exterior case, where you had this space in the embedding space that you could alter your closest point extension in. So you were free to alter it there, but now you need to simultaneously enforce the PDE and the boundary condition in this chunk of embedding space. So what we do is define the interior boundary set, which are grid points in this thick black region, and we denote that with omega of C, which is all the points now within a tube radius of C itself, so your actual interior boundary curve. And there was only one method that existed before, and what they were doing is to fix all the points in this omega C with the Dirichlet value alpha. But this is obviously only first order accurate, and it has a very large error constant. And it's because you're basically fixing all this red region of the manifold to have the fixed Dirichlet value alpha. And also this can obviously only handle Dirichlet boundary conditions when you have the actual value to specify. Yeah, and so we ended up realizing during our exploration of the interior and boundary conditions that you could actually do a little bit better than this and just fix one grid point instead with the Dirichlet value. It is, however, still only first order accurate, but it does improve the error constant. And again, it only applies to Dirichlet boundary conditions. But if all you need are first order accurate Dirichlet interior boundary conditions, then this approach is actually way simpler to implement than the general framework I'll discuss next. So yeah, I would suggest doing this if that's all you would care about. So for the general framework, consider the 1D curve embedded in 2D with an interior boundary point in white. Boundary conditions will require changing your stencils so that you can enforce the boundary. But as I mentioned, enforce the boundary condition. But as I mentioned before, we also need to impose the PDE itself in that same region. Therefore, the grid is duplicated. So it's duplicated near the white point to introduce new degrees of freedom, and that's in this thick black grid region omega C. And then that original black grid and the new interior boundary grid are partitioned based on the location of their closest points with respect to the normal manifold S perp, this green manifold. The two sides of the duplicated degrees of freedom are colored yellow and purple here. And then you connect each side of the new interior boundary grid to the opposite side of the original grid. And we're just warping into 3D here to show the final grid connectivity. But in actuality, we're still in 2D. It's just a non-manifold grid now. But here's the important thing, is that now you have space in these purple and yellow regions to enforce the, to alter the closest point extension to impose the interior boundary conditions. So the exact same techniques for exterior boundary conditions are used in these yellow and purple regions of this non-manifold grid. Unfortunately, there is one problem. So this is exactly how you could implement it if you had an orientable manifold. And it's great as an illustration to understand what's going on. But for a manifold, so to construct the non-manifold grid directly, it only works if a global partitioning of the grid can be obtained. So if you have a non-orientable surface and your interior boundary loops fully around, you have this inherent flip in the curve, and so it's actually impossible to divide your space with a global partitioning. So what we do instead is we locally check each stencil for grid points whose closest points cross the green normal manifold. This example shows an interpolation stencil in orange and the finite difference stencil in red that are intersecting that green normal manifold. And modifications are performed on a per stencil basis if your closest point has crossed. So you enforce the boundary condition equations if that grid point crossed. And when I say crossed, it's with respect to what we call the stencil director. So the stencil director for an interpolation stencil is the interpolation query point, and the stencil director for the finite difference stencils is the closest point of the stencil center. So to successfully apply our approach, we must be able to tell if two closest points are on opposite sides of S-perp, this green normal manifold. So if you consider 2 points x1 and x2 with corresponding closest points CPS and CPS, a naive thing would be to see if this line segment intersects with some explicit representation of S-perp, like build a mesh of the green normal manifold, and then check to see if there's an intersection. But you can do something simpler. So we instead compute the closest points to the boundary curve C also, and then these orange vectors will point in opposite directions if CPS of x1 and x2 are on opposite sides of S-perp. So it just becomes a simple check on the sign of the dot product between the vectors. I will refer to these vectors as CPdiff since they're the difference between the closest points on S and on C. Okay, so in the overall matrix equation, you add extra rows and columns for the new interior boundary condition degrees of freedom in green, and recall that each row is for a specific grid point, which in this case is the index of the stencil director. The non-zero column entries correspond to stencil weights for each grid point that is part of that stencil. And so the non-zero column entries will get moved to their corresponding interior boundary degree of freedom in the green region if the closest point had crossed the green normal manifold with respect to the stencil director. And so there is a key difference here to the exterior boundary conditions, which is that there now needs to be modifications with the Laplacian matrix because you're actually changing the connectivity between your stencils to new indices. And the stencil weights for Laplacian, they do stay the same, but the stencil weights for the interpolation matrix will change to make sure that you're imposing the actual boundary condition you want to impose. So that'll depend on if you want to do like Dirichlet or Neumann or first and second order accuracy of the actual boundary conditions. So one thing to point out though for open curves is that you actually don't apply the boundary condition modifications outside the endpoints of the open curve. So the boundary set omega c includes these half tubular regions in pink around the end cap, like around the endpoints of the open curve. But you actually only want the PDE to be being enforced there. And so yeah, we remove those from the actual or we just don't do the modifications for the boundary equations if your closest point to C was a boundary point, like an end point, sorry. So yeah, so there's this slight change for open curves. And you might think that it's like intuitive that maybe you need a change for points. So you have this white interior boundary point, but you actually don't have to do anything because what you're doing here is you want the boundary equations to be enforced at all points surrounding the white point. And as the stencil director changes, so you have this interpolation query point changing around the white point, you have a half space that cuts through with respect to that stencil director, and the boundary points end up filling up that whole space surrounding the white point, and the orange points are also spinning around there too. So yeah, you get both the PDE equations and the boundary condition equations all within that region. So the expected convergence rates were verified on a multitude of different analytical problems. We also checked, so what we checked was first order and second order accuracy of the methods to make sure they converged correctly, also for Dirichlet and Neumann boundary conditions. And we even checked, like, the one on the far left here is a discontinuous Dirichlet condition where you have two different values on either side of the white point. We also did a comparison using a closest point method approach against the mesh-based Cotan Laplacian. So we solved the Poisson equation on the Zook surface, level set surface with the exact solution u equals xy, and imposed a Dirichlet boundary condition on the white curve. It might seem like a simple problem with this exact solution, but the right-hand side function is actually this, and there's actually 50 plus terms in the numerator with different polynomial degree combinations. So it makes for a decent analytical test problem. And it's also nice because this surface has the property that it's both positive and negative curvature, whereas all other exact solutions that I know of, I've only seen like on positive curvature surfaces like the sphere, torus, and cylinder. But I'd be happy if anyone else has suggestions of problems that have exact solutions. So I'll show a comparison on the next slide, but just to recap all the different methods, we have a good and bad triangulation that I'll use with the Cotan Laplacian. And so these are the dashed lines, TG and TB. The main interior boundary condition framework that I talked about with first and second order accuracy are in blue and orange. And yeah, so then you also have the nearest point approach in purple, and the only existing approach by Euler and L in pink. Now I want to focus on how the meshes were actually constructed. So what we do is we have this poor triangulation TB as a starting triangulation, where you have these skinny sliver triangles, and then you do refinement. So we're subdividing by placing a new vertex at the midpoint of each edge and then projecting that vertex onto its closest point. And then this is the good triangulation with better shaped triangles, and after 4 rounds of subdivision, and we also do some Delaunay edge flips to improve the triangulation. So I'll start with a closed curve for the interior boundary condition comparison. The first thing I want to point out about the comparison are the axes here. So you have computation time versus error and memory versus error. This is because you cannot directly compare the mesh resolution with the grid spacing of the closest point method. Because of what we discussed earlier, depending on the convexity of the surface, 2 neighboring grid points can have closest points closer together or further apart. And with a mesh, it does actually depend on the actual, like it does correspond to basically distances within the surface. An approximation of it at least. The closest point method, yeah, so we have that, like, the best, for a fixed computation time, the closest point method has the lowest error, shown in orange, the second order one. And the same behavior is seen for the memory usage here. So the first order and the nearest point approaches in blue and purple are basically the same, and they fall between the green and red dashed lines. And you have a question?
Yeah, sorry, quick question. So since you are working with a triangular mesh, so when you compute the closest point for your grid nodes, do you compute it as if it's projected onto a flat triangle surface, or is there any other way that you compute the closest point?
Yeah, so you can do different things depending on what information you have available. So in this comparison, we're actually computing the closest points with the level set description. Yeah, and so, but you could just compute it to the actual mesh also. Yeah. And yeah, so the reason why the first order accurate blue and purple lines end up between the good and bad triangulation is because those are also first order accurate. And this is because we didn't do anything fancy to enforce the boundary condition, but finding the nearest vertex in the triangle mesh. And this is because we're just looking for like a baseline here to kind of get a rough idea of where the closest point method lies with respect to mesh-based methods. So for an open curve, remember the first and second order methods are slightly different because you don't include these grid points in the caps near the endpoints. So comparing again the error for fixed computation time and the memory usage, you can see that the first and second order methods are in blue and orange have the lowest error. And yeah, so that's basically the only difference here is that the blue curve for the first order method became better than the mesh-based good mesh solver. But yeah, so the nearest point and orientable methods in purple and pink, they did not change their relative positioning with the dashed lines, and the blue one got a bit of order of magnitude better. And now for a point interior boundary condition, the pink orientable method also is again the worst. It has the largest error constant, and you can see that the error of the first order method in blue is only slightly better than the nearest point approach in purple, but they're both roughly an order and a half, 1.5 orders of magnitude better than the pink. The big difference here in the story is actually with the mesh-based method. So the bad triangulation still follows the red line, still follows first order accuracy with the purple and blue lines, but the green one now is slightly better than our second order method. And this is because the mesh, we chose a boundary point to be a mesh vertex. And so now the mesh-based method can obtain second order accuracy. But the nice thing here is that the closest point methods, they're agnostic to the quality of the mesh because we are actually computing closest points with the level set representation. And so you don't have this problem with the red poor triangulation. Okay, so we now know that the method converges as expected. It has computation and time and memory usage similar to mesh-based methods, which are probably the most common approach. But before getting into the geometry processing applications, I'd like to recap the benefits of the closest point method. So, as I just mentioned, it's independent of mesh quality. It applies to any manifold representation that allows closest point queries. It doesn't matter if the manifold is orientable or not. It can be open or closed, any dimension, any codimension. So it's very general. So this gives us a powerful framework for PDE-based geometry processing, since it only needs one implementation for numerous representations and different types of objects. So let's just look at some applications now. So diffusion curves were originally developed as a compact representation of images, where you just define the colors on the curves and then solve the PDE to get the color over the whole surface and over the whole plane, sorry. And so this can be extended to surfaces, though. And you just replace the Laplace equation with the Laplace-Beltrami equation. And the Laplace-Beltrami equation is solved independently for each color channel, red, green, and blue, where the subscript I is denoting that color channel. So the white curves here are the Dirichlet conditions. The black are the Neumann conditions in this example. So you can impose both of those. The B is the binormal to the curve, which is analogous to what the conormal would be for the exterior case in this interior boundary condition case. And so the whole surface on the right is colored from the boundary conditions on the left, and you can see the color gradient in the band can go across the Neumann black curves. And that's because you're only blocking the color from going across that curve, but it can freely travel within each kind of rectangular piece. This is an example on a non-manifold object. So you have a Dirichlet interior boundary. All the white curves are Dirichlet interior boundary curves, and the color spread out. And you can see from the zoom in that the blue and green are spreading across this one-dimensional curve from the torus to the sphere. So in sake of time, I'm going to skip the description of the actual methods, but just show some results. So the vector Laplacian, this doesn't make much sense without that, though. Okay, so you have this heat equation for vector field design, and what we're doing is solving the heat equation, and then after each time step of implicit Euler time stepping, we project the vectors onto the tangent space. And so what I was doing here is showing that it's different than doing parallel transport like the vector heat method. You have this smoothing across the cut locus, which may be beneficial or not, depending on the application that you want it for. And you can see that the norm of the dot product is really close, except on the cut locus here, because yellow is norm 1. And here's an example where we're designing a vector field on a Lucy statuette using a sparse set of directions. And we're using the nearest neighbors as the closest points to the point cloud. That's only accurate if you have a dense enough point cloud. So at the beginning of the course, I discussed, or I showed a paper that you can use for more general point clouds. All the boundary conditions here are Dirichlet boundary conditions, specifying the directions. And in this example, on the Mobius strip, you can see a Neumann boundary condition in this zoom-in region, where your Neumann condition is blocking the direction change across the white curve. Okay, so geodesic distance, we end up using the heat method for geodesic distance. And so that involves 4 steps, or 3 steps really. So you do short time for heat flow, you compute the gradient and normalize it to get this normalized gradient x, and then you solve a Poisson equation to get the scalar distance field. Here are some examples of computing geodesic distance to the interior boundary curve shown in black. Our closest point method approach provides a single implementation for multiple representations, which previously required a different implementation for each. So there is some caveats to getting the heat method to work properly with the closest point method. I won't go into the details now, but just know they exist because it was the first test problem I used, and it led me into some rabbit holes. But there's been follow-up work by others too on this problem. So another application is with reaction to fusion textures. So you can solve this reaction to fusion system for U and V to get patterns that form from random initial conditions. And you can use both Dirichlet and Neumann boundary conditions also. And so here is a texture on a fish from solving the reaction to fusion system. We're only showing the reactant U, and it's colored yellow if there's high concentration and purple if there's low concentration. Interior boundary conditions are used to control the texture, so you can get like Dirichlet conditions can control the stripes, and Neumann conditions on the top of the curve on the dorsal fin can give you orthogonally intersecting patterns to the actual boundary curve. So a final application is a little different from the rest. So it involves computing a harmonic map between two surfaces, S1 and S2. And harmonic maps are minimizers of this energy, which then you can show you have this gradient descent flow, which is basically the heat equation on S1, but you have this projection onto the tangent space of S2. And we showed in previous work that you can decouple S1 and S2 by iterating at each time step the solve of the heat equation just on S1, and then that gives you U tilde, and you project U tilde onto S2 by just computing its closest point. And so here's an example where the mapping is used to transfer a texture from S1 to S2, while enforcing that the white landmark curves match up. And that's a Dirichlet condition being imposed. So comparing, if you just did the harmonic map itself without that white curve, you can see that the map is stretching and compressing near this white curve, and that's expected because you know that you need to stretch and compress to deviate from being harmonic to enforce the actual curves aligning. Okay, so next I'll talk about ways to improve the efficiency of the closest point method. And yeah, so there's been some work for improving the efficiency that we already discussed. And there's also been a couple papers that have looked at improving the efficiency of the solvers. So there's been work in the paper on the left with a multi-grid solver, and on the right, a domain decomposition method that can exploit distributed parallelism. But there's actually another way to improve runtime in certain cases without using more advanced solvers. You can use spatial adaptivity to make the actual matrix system itself smaller. So previous closest point method work always used a single uniform grid spacing in the embedding space, but obviously this can be extremely inefficient for manifolds that have pieces that are geodesically distant but are close together in Euclidean space. For this spiral example, the smallest resolution shown in the rightmost zoom, that would have to be used over the entire spiral previously, which would lead to many unnecessary grid points and thus a bigger matrix system and a higher computational cost. So I'll discuss a way to couple overlapping computational tubes that have different resolutions so we can have fine grids in some regions and coarse grids in others. So what we do is break the manifold up into multiple subsets. Each subset of the manifold is given its own tube Euler neighborhood, N of S1, N of S2, N of S3. And my key insight was a way to join each subset using the overlapping regions. So these N of partial S1, N of partial S2 is this dark red, and N of partial S3. And so if you consider just one boundary between two subsets, any point x in the boundary subset, N of partial S1, will have the closest point, CP of partial S1, at the boundary point itself, this white point. So if you denote the closest point extension as E1 US, then that's US of CP of S1, which is of US of CP of partial S1. But obviously for the global problem, that's incorrect. So this white vector is definitely not in the normal direction, and you should be extending data constant in the normal direction. So what you actually want is this blue point, and what we do is redefine the extension E1 to use the bordering subset CP of S2. So E1 US becomes E2 US, which again is US of CP of S2. So in words, you're just, for every point in a boundary subset, you use the closest point extension from the bordering subset instead of the naive extension. And this is also nice because we're using overlapping grids, and that's exactly what the domain decomposition paper was using. So it should be pretty straightforward to actually use adaptivity also with the domain decomposition solver. Yeah, and so here are some examples. So adaptivity can be based on many different criteria. In this example, we're refining the grid where the solution gradient is large. So we're solving this Poisson equation on an arc with Dirichlet boundary conditions, and these are approximately -1 and 1. And the exact solution is this hyperbolic tangent function that has a large gradient near the center of the arc where it transitions from -1 to 1. And so we compare using this adaptive grid with varying resolutions in just the red region with using that finer resolution over the entire arc. Okay, so this is the convergence study, and we can see that the uniform and adaptive grids are nearly identical. The results are nearly identical because the orange is completely on top of the blue line. And if you divide the quantities of the uniform grid approach by the corresponding adaptive ones, we see that as the grid resolution in the red region is refined, the LU decomposition time and the number of degrees of freedom in the linear system are scaling together and improving by about a factor of 10 at the finest resolution, and the solve time continues a little further, reaching almost a 14x speed up. Another criteria for adaptivity is the local feature size, which tells us how much room in the embedding space we have for the grid. In this example, the resolution of the grid must be finer in the region where the actual spiral sheet wraps around, and it can be coarser further to the right. We solve this screen Poisson equation with homogeneous Neumann boundary conditions, and the exact solution is this multiplication of cosines, where you have the S parameter, which goes around the spiral, and the Z parameter is the depth of the sheet. And here's the adaptive grid, and a zoom in of it. And so here are the results. On the left is the solution with a uniform grid using the finest resolution in the adaptive grid. And the result on the right is the adaptive one. And the two are visually indistinguishable, but the uniform result takes 22 minutes to compute, whereas the adaptive one takes 76 seconds, roughly a 17x speed up. So there's lots of interesting future work for the closest point method. I'll go through some open problems that I think are important. Since we're just talking about adaptivity, the examples I showed use manually selected subsets just to verify that the overall discretization worked with these overlapping grids of different resolution. But to choose these subsets in an optimal way is a really interesting open problem. What you'll want to do possibly is minimize the number of grid points and subject to some constraints. It could be local feature size, curvature, the gradients. It could be error estimates in the solution and some user prescribed tolerance. And the number of grid points can be estimated from the volume of the tube divided by the volume of a single cell. And yeah, so you can use Weyl tube formula to get the volume. So 1D curve in 2D is this. 1D curve in 3D is this equation, and 2D surface in 3D is the volume of the tube is given by this equation. But I guess the main open question here is like, how do you actually compute this discretely with the information that you have, and what kind of optimization problem and how are you going to solve that problem? Somewhat related to that same idea with adaptivity, but more generally just having a grid-based closest point method, it would be great to know what the grid spacing should be before you actually solve. So in this example, we ran the solver with H on the left, and we see that there's unwanted artifacts with the purple on the head, and in the zoom in, there's like a blue dot inside this red region. So when we half the actual grid spacing, we see we get the desired result. But this wastes a lot of time of like solving, manually checking, solving with a smaller resolution. And so, yeah, having a way to actually a priori determine the grid spacing would be interesting future work, which might depend on error estimates or medial axis avoidance or something else completely. Another approach to improve efficiency, besides adaptivity and knowing what H should be before you solve, is apparent with bottleneck regions. So these are regions, like I said before, that you have geodesically distant parts of your manifold close together in Euclidean space. What you could do here, instead of just using the closest point extension, is you could consider extending multiple values to a single grid point. So you have this red value and this orange value, both extended to a grid point. And then when you have stencils that are closer to the red surface point, you use that value, and then and then if you have a stencil that's closer to the orange point, then you use that value that's been extended. So, yeah, the big question here is how to actually compute all the orthogonal intersections, like all the orthogonal intersection points to the surface instead of just the closest points. Okay, and another interesting problem is how to handle sharp features and discontinuous solutions. So the closest point method theory is based around having smooth manifolds and smooth solutions. Convergence order does degrade, like I mentioned before, when either of these aren't satisfied. And so the first paper on the left used Weno interpolation to reduce the effects of the sharp features and discontinuous solutions. And what Weno interpolation is it uses two different degree interpolation polynomials, and having this information, you can actually detect and reduce the error that comes from discontinuous issues. The middle paper uses radial basis function discretizations, and it actually does handle sharp features directly, but yeah, the way it's set up, they can only achieve first order accuracy. And so you can just use the standard closest point method on the grid with second order approximations, and you'll get, I don't know, like 1.5 order of convergence, depending on what the actual problem is and the sharp features. But if you can only achieve first order accuracy with the method that's actually handling the sharp features directly, it's kind of pointless. But maybe there's ideas there to actually build on. And this third paper, it uses ideas from algebraic geometry to actually remove isolated singularity points by lifting to a higher dimensional space. So it's great in that setting, but it doesn't work in general for all surfaces and sharp features. But you could think about handling a sharp feature by decomposing the manifold into piecewise smooth manifolds, and then construct a a tubular region around each piece. But yeah, so the main question here, though, is now how do you actually couple the two pieces together so you're solving the correct global problem? Okay, and yeah, so there's other differential operators that haven't been considered with the closest point method. So like the connection Laplacian, this Dirac operator, it would be really interesting to see how you would actually handle those. There has been this poster a few years ago from SIGGRAPH Asia that like made the theory a bit more general in the exterior calculus setting. So maybe ideas around there can be used in future work. And so yeah, so throughout this course we talked about grid-based methods, but you might want to have a solver that is actually continuous using some neural network. And the grid-based methods have this inherent resolution dependence that is a limitation. The PDE, so the paper on the left replaced the closest point extension step with a neural network. But the PD itself was still solved on a grid with finite differences. But the paper on the right, it's not using the closest point method ideas. It's using tangent space projection definition of your manifold differential operators. But it uses a PD solver based on a physics-informed neural network. So maybe the ideas of both of these papers can be combined to get a more general solver for all different types of manifolds and fully continuous. Another approach for a continuous solver is to use Monte Carlo methods. And yeah, the first paper on the left, it was the first one to actually solve surface PDEs with Monte Carlo methods. And what they do is use a conformal map to set up a spatially varying coefficient equation like PDE and solve that. And then we developed a Monte Carlo closest point method that could directly solve it on the surface without the need for the conformal map. But there is a key limitation in the right paper also that ends up on certain problems giving you a biased estimator, and it would be interesting future work to see if you could improve that. Okay, so overall, I just want to conclude by saying like the closest point method itself is actually relatively new. So this is the first paper, it was published in 2008, whereas the finite element method can be traced back to 1941, and the first surface finite element method was in 1988. So there's been a lot of extra development on other types of methods, but I think the closest point representation has a lot of unexplored potential, not even just in terms of PDE-based geometry processing. But this course, we explored a powerful framework for PDE-based geometry processing that has similar computation times and error to these mesh-based methods, but it's much more general. It allows any representation that you can have closest points queries to, works for general manifold types and in any dimension or codimension. And so I just want to give a special thanks to my collaborators during my PhD, Ryusuke and Haoje, Toshiya and Merdul, and my supervisors, Steve and Christopher. And I'd be happy to answer any more questions. If we have time. I guess we have 1 minute. Okay.
How does your method fare with, say, surface varying problem, where you're also moving the surface? That's the underlying geometry.
Right. Yeah. So there was an application in one of the I'm not sure which the first author was, but Westerman's papers, where they actually did surface fairing. To get it to work efficiently, you need to be able to recompute the closest point function as the actual representation changes. So the main contribution of that paper was to do the closest point computation on a GPU. But yeah, I guess there's no issues with it with respect to that except the efficiency problem. If you could do it like a level set fluid simulation where you actually propagate the level set field itself, that would be interesting. But I mean, Steve had mentioned to me they looked into that in the past, and there were issues with like codimensional and non-manifold structures coming up as you actually change the field.
Sorry, and I just have more questions. I guess I'm also happy to just stay if we want to, and
yeah, maybe we could do that. I mean, it's past time now, unless there's other quick questions.
One quick one. I was wondering, because like you discussed quickly the vector Laplacian, but like is it bound specifically to the Levi-Civita connection, or is there a way to?
Sorry, I missed. So the vector Laplacian.
Yeah.
Is it specific to?
Like, does it make an assumption on the connection that it chooses, or is there a way to choose a specific connection on the surface and to extend it to the closest point method?
I would be curious what the connection actually is under this assumption, but like it's basically a splitting scheme. But I've never actually thought too much about it, what the actual connection would be instead of the parallel transport one.
Okay, thank you.
Thank you.